All right, chemists, we're just going to do some practice problems in this video, trying to combine some of the newer reactions we've learned, and you'll notice some of the older ones, even from last semester. We're going to start off with some synthesis schemes. I see a bunch of reagents in front of us, and they're asking us to fill in the various products. So let's just zoom in and take it one step at a time. First off, NBS. NBS stands for N-bromosuccinimide. And this is a source of Br+, but we learned this as a source of doing radical bromination. That's what this is, radical bromination, radical substitution. So how do we figure out radical substitutions? Find the best radical, in this case, the allylic spot, and you do a substitution reaction. So I'm going to replace one of those hydrogens with a bromine at the allylic spot. Next up, should have no trouble with that, magnesium metal forms the Grignard. Then we get to some newer chemistry. Grignards will react with carbon dioxide to make a carboxylic acid. If you forget how that happens, remember how we think of Grignards. Grignards behave like negative charges where the metal's attached. And then if I picture a carbon dioxide molecule, the arrow pushing would look something like the negative carbon attacking the CO2, sending a pi bond up, and you get a new carbon-carbon bond. The double bond to the oxygen is still there. Now there's a single bond to the oxygen. My arrow pushing down there means I have a negative charge. Oh wait, there's H+, so I get an OH. So that's how you make your carboxylic acid. One of the best ways to make a carboxylic acid, notice it adds a carbon. CO2 is a great way to add one carbon. And lastly, we get to some new chemistry, or lastly in this row, this is just chlorination, turning the OH into a Cl. It's actually the same reagent we used to turn alcohols into chlorides. It also works for carboxylic acids to make acid chlorides. Okay, let's see if we can get the second row. So here we have an alkyne, and this is an old reaction from semester 1. This is hydroboration of alkynes. And remember how that works. It means you add an H to the more substituted carbon and an OH to the less substituted carbon. That would give you an enol, which does not stay put. It tautomerizes to a carbonyl. So really what I get is a carbonyl on the less substituted carbon. In this case, that means I'm going to get an aldehyde. And notice the benzene is just along for the ride. Next up, we get the Jones oxidation. We learned that this is a way of oxidizing primary alcohols into carboxylic acids. It also works on aldehydes. It oxidizes the aldehyde to a carboxylic acid. In fact, the reaction we learned that takes alcohols to carboxylic acids actually goes via the aldehyde. We just never did that in its entirety. And lastly in this row, we have an esterification. This is a Fischer esterification. So that will combine your alcohol and your acid. You'll lose a water molecule. I'll lose OH and H, and then you get a new carbon-oxygen bond. So I'll have my phenyl still along for the ride, my carbonyl, and now it's an ester with, looks like 3 carbons attached. 1, 2, 3. I'll just draw it like that so I can fit it better. So there's your ester. Okay, let's keep going. Old chemistry again. This is oxymercuration of alkenes. Alkene. Oxymercuration. This is Markovnikov. It does an addition to the alkene. You'll get an H on the less substituted and an OH on the more substituted carbon. And I'm going to predict, since I start to see double in the next step, that we have excess of this. and I'm going to hit both alkenes. It's symmetric, so if I only drew one, that'd be fine. And if you only draw one, that's fine too, but I'm going to pretend it gets rid of both. And then you get a diol. And now we get to some new chemistry. Alcohol plus, this is essentially an acid chloride, sort of a double acid chloride. This is called phosgene. It's a very dangerous molecule. It used to be used for nerve gas in World War I. For our purposes, it's an acid chloride and an alcohol, which should give me an ester. So if I imagine making an ester out of one of the alcohols and the acid chloride, I'd be there. However, as soon as I do that, I realize I still have another what looked like acid chloride and another alcohol. So this is going to cyclize and make a double ester, which is no longer an ester. This is called a carbonate. Think of carbonic acid, which is what this molecule would look like if it was capped off with H's. Okay, part D, repeat of part A, NBS, radical bromination again. We're looking at the allylic position. So take away one of the hydrogens on the allylic carbon and put a bromine in its place. And then we get another repeat of what we saw up above. This is Grignard formation, reaction with CO2 to make a carboxylic acid. You add a carbon, and the H plus just caps that O negative off as an OH. I'm going to rotate my molecule so I can fit it a little better. I get one new carbon and an OH, and then another Fischer esterification changes the OH into OR, in this case O-ethyl. And we're actually not done. Diazomethane, what the heck does this do? Well, let's recap when I saw diazomethane. There's really only one time I've seen it. It was a reaction of a carboxylic acid. And treatment of a carboxylic acid with diazomethane actually makes a methyl ester. Really clean, useful reaction for making specifically a methyl ester. But I need a carboxylic acid to do that, so I really don't even know what the point of this one is. This is no reaction. I guess the point is just to remind us that not everything always causes a reaction. Okay, let's wrap up with some synthesis. 3 quick synthesis examples. The first one wants us to make an alkane from an acid. And I notice I need extra carbons. I only have 3 carbons in this starting material. Looks like I have 5 in the product, so I need to bring in 2 extra carbons. And based on the branching, it looks like I need to bring them in as 2 1-carbon pieces. So let's go backwards and ask ourselves, how can we make an alkane? Alkanes are those functional groups, is that one functional group that you have to think of something else being there that you got rid of. For example, we could have had an alkene prior to this. You could hydrogenate an alkene. I'm just drawing one possibility. It also could have been a ketone. I could have Wolff-Kishnered the ketone down to the alkane. I'm going to go with the alkene for now because alkenes can come from alcohols via dehydration, and an alcohol can come from organometallics. I could imagine bringing in those 2 methyl groups as methyl organometallics and an aldehyde. Sorry, not an aldehyde, an acid derivative. Remember, acid derivatives plus things like Grignards react twice. The Grignard will attack the acid chloride, electrons go up, come back down, kick out the chlorine. You get an intermediate ketone. The Grignard attacks the ketone, electrons go up, you get a alkoxide with a negative charge, which H plus will give you the alcohol. So we're effectively there, because I can make that acid chloride from my starting carboxylic acid. So now let's go forward. Let's draw out the acid. I want to convert that into my acid chloride. So SOCl2. And then I want to react that with methyl Grignard. I obviously have to bring in methyl Grignard. That's a commercially available reagent. There's no problem there. At this point in the course, you're free to bring in small building blocks as reagents. And if you're not sure if it's valid or not, I would say a good rule of thumb is if it's only a couple of carbons and there's only one functional group present, you're safe to assume that it's either commercially available or pretty easy to make, that you could just use it in a synthesis. I want to turn that tertiary alcohol into an alkene. I'll use POCl3 to do that. That should give me the Zaitsev. Luckily, it doesn't matter because I'm just going to hydrogenate the alkene down to the alkane. Kind of ridiculous to make an alkane like that from carboxylic acid. No doubt this will probably be a gas from a liquid, so it's going to be very hard to trap, but just a good reaction review. Okay, let's try a few more. In B, we have a ketone, cyclopentanone, and I want to make something with an alcohol and an acid, so I want to make a hydroxy acid out of this. I'll check my carbon count real fast. We have 5 carbons in the beginning, and it looks like I have 1, 2, 3, 4, 5 in the product, so I actually don't want to gain or lose any carbons. So I'm going to think backwards. How do you make carboxylic acids? Well, you can make carboxylic acids by oxidizing alcohols, so perhaps I could use that, but it's going to be really hard to oxidize one alcohol and keep the other one, so I actually don't like that idea very much. So instead, I'm going to think about making a carboxylic acid from a carboxylic acid derivative. For example, an ester. You can hydrolyze any carboxylic acid derivative, and it'll become a carboxylic acid. So if I have some type of ester, I would get my carboxylic acid. The hydrolysis of an ester actually makes an alcohol. Whatever your R is becomes ROH after the hydrolysis. So hang on, why don't I just use this as my R group? Which really means, and perhaps this is tough to see, that this hydroxy acid could come from that ester. And I intentionally drew it hideously so you can see. Actually, I drew it incorrectly now that I think about it. I accidentally gained a carbon. And there we go. 1, 2, 3, 4, 5. There we go. That's an ester that I would want. This looks like the bottom half of an eggshell. Let's redraw this. If you count your carbons and the oxygen, you'll notice this is a 6-membered ring, lactone. And the point of this is that it's an ester, it's an acid derivative, so just hydrolysis would give me that acid as a product. You can go back and look at 12.1 and 12.2 to see that chemistry. What good is that, you might be asking? How do I get that lactone from that ketone? You get it in one step. It comes from the Baeyer-Villiger. This is a Baeyer-Villiger example. May not be the only way to do this, but we've got it, and it's going to be fast. 2 steps. So let's redraw our ketone. The Baeyer-Villiger oxidation needs a per acid, so MCPBA. I know that makes epoxides with alkenes, but if you have a ketone, you actually get your ester, in this case, a cyclic ester. And then hydrolysis, H3O+. Or saponification. If you did this and you're checking your answers, saponification is also good. That's base followed by acid. That also converts esters into carboxylic acids. So you'll get a carboxylic acid, but you'll also get this alcohol tethered to the same molecule, and that's actually the product that we want. Okay, one more. Let's do our last one here. So we have our product is an amide, and our starting material looks like an aldehyde and a nitrile. So let's go backwards because I don't see it in the forward direction yet. Amides they're made from amines and carboxylic acid derivatives. So actually 2 options. You could have the amine, which in this case is ethylamine, and then a 3-carbon acid derivative. You can either use the carboxylic acid itself. That means you need to use a reagent known as DCC. I'm not sure if we've learned that yet, but if you did, that's fine. Or alternatively, you could use the acid chloride. That works just as well, if not better. Now the question is, how do I make the acid chloride from the aldehyde, and how do I make the amine from the nitrile? So I got to go backwards for both of these. I'll start with the acid chloride. Acid chlorides can be made from carboxylic acids, SOCl2. Acids can be made from the oxidation of an aldehyde. Jones oxidation, as we saw up above, will take an aldehyde and turn it into an acid. So now I just need to make this nitrile, and we're in luck. That's a two carbon amine. I need to make this amine from a 2-carbon nitrile. You can reduce nitriles to make amines. The carbon-nitrogen triple bond can be reduced just like a carbon-carbon triple bond. So we're done. We just need to write this out in the forward direction. So I'll start by making my nitrile turn into an amine. That's H2 and palladium. And then separately, I'll take our aldehyde. I'm going to oxidize it with the Jones oxidation. That gets us to a carboxylic acid. Then I'm going to treat that with SOCl2 to make the acid chloride. And then we just simply react that with the amine. There's no other reagent other than the amine. Acid chloride plus amine makes amide. And if you're really particular, which you should be at this level of the class, you actually need 2 equivalents of that amine, because remember your byproduct is going to be HCl. So that's immediately going to get consumed by the amine. So it's good to do this if you have a relatively inexpensive amine. And then your byproduct is ethyl ammonium chloride, a salt. Okay, so there's a couple of synthesis problems and some reaction review just to combine what we've learned in this unit with some older reactions and apply them to syntheses.